Hello everyone. Good evening. How was your quiz?
Good.
Good. How was the paper? How did you find the paper?
Moderate level.
Moderate level. Yeah, it was easy. Okay. So so this week we have both week five, week six, and week seven deadline. So we'll do both. So we'll be doing both week six and week seven this week. So today let's start with week six.
Week 5 already discussed, ma'am.
Yeah, week five deadline is over, right? Last week.
Yes, yes.
Yeah. So week five is done. So today we'll do week six. Yeah, okay. So will be discussion of quiz one. Quiz one discussion. So did you receive the answer key?
Yes, ma'am.
Okay. So quiz one discussion will schedule in this week sometime. Not today. So okay. So I'm not able to write somehow. Is it okay if I cover the go through the slides? My pen is not working for some reason. Will it be okay with all of you if I cover the slides?
Yes, ma'am.
Okay.
Ma'am, try to fix this issue, ma'am, with pen,
Yeah. Uh,
because from the slides, not much better understanding to us.
yeah, I'm just trying.
Ma'am, just take a few minutes for this.
Okay, okay, sure, sure. Thank you.
Ma'am, start the session.
Actually, ma'am, fixing this e-pen, so can you wait for some time?
Um, let me join back. I think I'll join in 2 minutes. Let me join back and see if it's working. Hello everyone. Sorry for keep you waiting. All right, so we'll start week 6 now. So in week 5, we had started linear regression, right? So what we have seen so far is we had defined the linear regression problem, and we had seen that we wanted to minimize, the goal was for us to minimize the sum over W transpose Xi minus Yi whole square, where I is varying from 1 to n, and this is over W. And we were able to write it equivalently in terms of matrices as norm of X transpose W minus Y whole square. Okay. So this was our goal. This is our goal in linear regression problem. Now moving forward in this week, like what we are going to see is like whatever the least square solution that we have seen, and what is the probabilistic view of the linear regression that we have seen, like how can we proceed it further, and see what all different kind of like how does it change if we change certain things in this problem. Okay, so when we saw it probabilistically, like probabilistic view of the linear regression, there we had so again the problem was that my since a linear regression problem, you will have a feature space and you will have a label space. So the feature space X, which belong to RD, and Y belongs to R, and this is my data set. So my data set is X1 Y1, X2 Y2, so on till Xn Yn. So we have n observations, and where X belongs to RD and Y belongs to R. So what we have assumed is that my labels are generated using this distribution, which is Y given X the feature space is generated using this distribution, which is W transpose X plus epsilon. Okay. So W we know is a parameter space, and they are something which is, I mean, this is something that we wanted to estimate, right? So W is what we wanted to estimate, and what is my epsilon here? Epsilon is the error term which followed a normal distribution with mean zero and variance sigma square, right? This is a linear regression problem in probabilistic view. Now we want to estimate W over here. So we had used the likelihood to estimate the W. We had used the likelihood. Then we found the ML estimator, and what we had seen is that my W hat ML that turns out to be, so W hat ML turns out to be the same W star which we had seen for the when we did the least square solutions. So the solution turns out to be same as W star, which is XX transpose inverse XY. So it turns out to be the same solution, which was my W star initially. Now we have this solution with us, and now we want to see like how good is this estimator. So the estimator that we have obtained in W hat ML, we want to know how good is this estimator. So that is where my week 6 starts. So week 6 starts here, and the very first thing that we will see is the goodness of my MLE estimator. So okay. So what we found is that my W hat ML is XX transpose inverse XY, right? And when we were finding out this, like the way we have found this estimator is by assuming that my error term followed a normal with mean zero and variance sigma square, right? So if the error term follows a normal with mean zero and variance sigma square, and I'm saying that y given x follows this distribution, y transpose x plus epsilon, then what should be the distribution of y given x? Epsilon is a normal distribution. So what should be the distribution of y given x? Any guesses?
Normal W transpose X.
Normal with mean W transpose x, and variance stays the same, which is sigma square. Okay. So this is what we get. So we have y given x, This follows a normal distribution with mean W transpose x and variance sigma square. So here W hat ML was an estimator of W, and W is something which was not known to us, right? Because W is what we wanted to estimate. It was unknown, but some fixed quantity. And uh, so and that's how, like, when we estimated it, we found this W hat ML. Now to check how good this estimator is, we are going to look at this term, which is to check the goodness of this estimator, we will look at this term, which is expected value of W hat ML minus W. So this is basically, so W is your true, this is your true W, right? True parameter. And W hat ML is something that you have estimated. So W hat ML is a random quantity for us, right? W hat ML is random, which will, like, depending on what sample you take, you will get different W hat ML estimate. So we are interested in checking like how does this W hat ML uh, W hat ML and W varies. Like what's the expectation of this W hat ML minus W ka norm square? How does it look like? So when we solve for this problem, I mean this proof we are not going to look at. So when we solve this problem, what we find out that this expectation and this expectation we are trying to find out to check for this is for to check the goodness of the estimator. So to check goodness of W hat ML in estimating my W. So this term over here, it comes out to be sigma square times the trace of XX transpose inverse. Okay. So this is something which we get. Like when we solve for this, I mean, when you do some calculations over here, you will find this term come out to be sigma square trace of XX transpose inverse. So different sample you take, you will get different values of this W hat ML, and that's how like when you try to find the expectation, you will get this term over here. So now sigma square is something which we don't have any control over, right? Because my data set is generated from a normal distribution with mean W transpose X and sigma square. And sigma square was the variance of the error term. So my epsilon followed a normal with mean 0 and variance sigma square. So sigma square is something which we don't have any control over. So like what we can do is we can work on this trace of XX transpose inverse. So how does this how can we uh, like work on this trace of XX transpose inverse so that we can reduce this value, right? We can so that we can reduce this value. So we'll see some different estimator, different like some alternative estimator apart from this W hat ML, and see how this term over here, which is mm, W hat ML minus W norm square, how does this term we can make it smaller and smaller. Okay. So, okay. So what we are going to do is we are going to make this is something also which we call it as a mean square error of, this is my mean square error of W hat ML. This is the mean square error of W hat ML. So, okay. Now we have to work on this trace of XX transpose inverse. Okay. So usually what is the trace of a matrix? Trace of a matrix is like you have uh, you have a matrix, you know its eigenvalues. You take you add all these eigenvalues and you get the trace of uh, the matrix, right? So that is what we have to figure out, like how do we choose this? Now, let's say you have some matrix for which the eigenvalues, suppose you have a matrix A, for which the eigenvalues are lambda 1, lambda 2, so on till lambda d. So, and think of this, not just A, let's say this is my XX transpose matrix. And my X was D cross N matrix, right? X was D cross N, X transpose would be N cross D. So we'll have a D cross D matrix. So we'll have D, let's say we have D eigenvalues, and these D eigenvalues are lambda 1, lambda 2, so on to lambda D. So now if we have to find the trace of this XX transpose inverse, this should be what? So trace should be
1 by lambda I, reciprocal of it,
yeah. So
and sum
if,
of it
hmm,
over all n
so
or
if we
d.
have to find the eigenvalues of XX transpose inverse, it would be 1 upon lambda 1, 1 upon lambda 2, so on till 1 upon lambda d, right? So the trace would be just sum over 1 upon lambda I, where I is varying from 1 to d. Okay, so this is the trace for my XX transpose inverse. So what do we get my expectation here? Or let me write mean square error of W hat ML. So in general, we want always my mean square error to be as low as possible, right? So for this linear regression problem, the mean square error for this W hat ML that we get is sigma square times trace of XX transpose inverse. So here this is sigma square times sum over 1 upon lambda I, where I is varying from 1 to d. Now, to now can we reduce this mean square error further by in some way, right? So this is our next goal. So what we will do now is, if we can introduce some new estimator, let's say some new estimator we introduce, and my new estimator, so W hat new is XX transpose inverse XX transpose plus lambda I. So we are adding this additional quantity lambda I inverse XY. So initially, like our W hat ML was what? It was XX transpose inverse XY. Now in this new estimator, we have added this term lambda I over here. Now, what will happen if, like, if we have this new estimator with us, how does the mean square error look like? This is what we have to see. So earlier, like if I think of this matrix XX transpose as some A, so the eigenvalues that we had taken for this matrix A was lambda 1, lambda 2, so on to lambda d. Now we know that if we add any constant to this matrix, right? So let's say I add a constant lambda I. So in this case, it's lambda I, right? So if we add this constant, all the eigenvalues will also get will get so in all the eigenvalues that we have, we will add this lambda term. That is what is going to happen. So the estimate the eigenvalues would be lambda 1 plus lambda, lambda 2 plus lambda, so on to lambda d plus lambda, right? So if this is the eigenvalue for my XX transpose plus lambda I, now if we have to find the inverse, So XX transpose plus lambda I ka inverse, then its eigenvalues would be 1 upon lambda 1 plus lambda, so on till 1 upon lambda d plus lambda, right? So this is these are the eigenvalues. Now if we find the trace, so trace of this term, which is XX transpose plus lambda I inverse, trace of this would be sum over 1 upon lambda I plus lambda I is varying from 1 to n. So the mean square error that you will get, the mean square error that you will get for this new estimator now is going to be sigma square times 1 upon lambda I plus lambda, where I is varying from 1 to n. So if we compare these two estimator, mean square error of these two estimator, we can see that that my mean square error of my W hat ML is going to be, sorry, this is going to be greater than the mean square error of my W hat new, right? So my new estimator uh, has lower mean square error as compared to the W hat ML. So by introducing this lambda I term in this, like in our previous estimator that we had found out, we are able to reduce the mean square error of the problem, right? And one thing to note down here, that this lambda is a positive quantity, okay? So lambda is greater than 0, greater than equal to 0. So now the question is, how are we getting this, how are we getting this new estimator? So our previous estimator, which is W hat ML, we had gotten it when we took this problem of linear regression and uh, using this, the way this W is generated through the normal W transpose X comma sigma square. So W is generated using this distribution, and we solved for the max MLE estimator, and we got this W hat ML. But now, how the question is, the new estimator that we are that is able to reduce the mean square errors by some factor by introducing this new term, which is lambda I in this estimator. So the question is, how are we getting this new estimator for a linear regression problem? So before, okay, so we'll look at like how do we get this new estimator. So this new estimator, which is given by XX transpose plus lambda I inverse XY, this new estimator is coming out if we use the Bayesian approach, right? Instead of ML estimation, if we use the Bayesian approach for our linear regression problem, we are going to get this new estimator. So if we use the Bayesian approach, what is the first thing that we need to know? The parameter that we wanted to estimate in the problem, in the linear regression problem, which was,
Excuse me, ma'am.
yes.
Sorry to interrupt, but actually I didn't get the concepts that you taught earlier. So could you scroll up a little? Maybe,
Yeah.
maybe because I haven't watched the video yet, so I'm
Okay,
having.
okay. Okay.
Yeah.
Tell me which part. More up.
So trace of x transpose inverse
Hmm.
will be summation 1 by lambda I. Okay. So it is because lambda I is the eigenvalue of x transpose.
Yes, this is what we are
We got
assuming.
this result.
Hmm.
Okay. And then mean MSE of
Hmm.
W hat ML we
Mhm.
got sigma squared summation I is equal to 1 to d 1 by lambda I.
Correct. Yeah.
Okay.
So this is see, this MSc of my W hat ML is given by sigma square times trace of XX transpose inverse. And the trace of XX transpose inverse is this, right?
Okay.
So
This,
we
could you scroll up from the beginning, actually?
Mm.
So I'm it's clear till week 5 because I haven't touched upon week 6 right now because I just came
you
from
have watched week 5.
yeah I've got
Okay.
till week 5 fairly easily.
Okay.
So so I got what we did here. Expectation. Uh, so y given x is normal double transpose x sigma square.
Mhm.
And here what we're trying to do is we are trying to find the expectation of w hat ml minus
Which is basically the mean square error.
the mean square, the expectation of the mean square. Okay,
Mhm.
and we got the result
Mhm.
to be. I'm not getting this part.
Okay. Um, See, we wanted to check like how well we had found out this W hat, right? We had found out our W hat ML, which is given by XX transpose inverse
That's
XY,
why.
right? Now, what is the sub W hat ML? This is an estimator, right? And what is it estimating? This is estimating W.
W hat, yeah, W.
W, right? So once you have an estimator, you want to know how good is that estimator, right? And when we are talking about the goodness of the estimator, it means we want to know like if you find the mean square error of uh, this estimator, you want this to be smaller, right?
Yes, ma'am.
You want to make your mean square error to be as small as possible. So the mean square error of this estimator W hat ML turns out to be sigma square. The proof is something that we have not seen. Uh, so this turns out to be XX sigma square trace of XX transpose inverse. Okay.
Okay.
So now what we want is we want to now sigma square is something which we don't have any control over. Why is that? Because what we have seen that the labels are generated using this W transpose X plus epsilon distribution, right? Sorry, normal with W transpose X, comma epsilon, sigma square. Where sigma square, where my epsilon was following a normal distribution with mean zero and varying sigma square, right? This one. My epsilon was generated using normal with mean
Yes,
zero
ma'am.
and variance sigma square. So sigma square is something which we don't have any control over, correct?
Yeah, it is the noise
Because
of
it
the
is the
given
noise.
data.
Yeah.
Yeah, it is the noise in the data. So
Okay.
if
It's
it
the
is a
noise.
noise in the data, then how do we? So sigma square we can't do anything, but we still have this trace term which we can try to reduce, right? Which is trace of XX transpose inverse. All right. So for this, I mean, in order to reduce the trace in some way, we have introduced a new estimator, and to see like uh, how that estimator, which is still estimating my W, how that is reducing my mean square error in some sense, right? So the trace of XX transpose inverse, this is like if we assume that my lambda 1, lambda 2 up to lambda d, they are the eigenvalues, then the inverse, if I take the inverse of this matrix xs transpose, if I take the inverse, you get this eigenvalue.
Yes.
And if I find the trace of this is going to be nothing but sum over 1 upon lambda I, right? Because trace is just the sum of the eigenvalues.
Yeah, clear, clear.
So now the MSE of W hat ML is turns out is coming out to be this. Okay, so this is what we have. Now, if we introduce, now what we said, let's just say if I have some new estimator for my, which is estimating my W. Okay, so again, this W hat new is estimating my W. Okay, so this is estimating my W, and if I define this in this way, so which is xx transpose plus lambda I inverse xy, then we know that like if you add some constant over here, your eigenvalues are going to look like this. So initially, if for xx transpose, if the eigenvalues were lambda 1, lambda 2, and so on, if you add this lambda I to this matrix, the eigenvalues would be lambda I plus lambda, basically lambda I plus lambda, right? Trace would be, sorry, the inverse would be just the reciprocal of all these eigenvalues, and trace would be sum of these. So the trace that we found for this new estimator, when we had this new estimator, so the trace of this matrix, which is xx transpose plus lambda I, when we found the trace of this matrix, it turns out to be 1 upon lambda I plus lambda. Okay, so now just compare these two, which is now uh, earlier my MSE of W hat ML was sigma square sum over 1 upon lambda I, and the new estimator that we have found, the mean square error for this is sigma square sum over 1 upon lambda I plus lambda. So here lambda
So
is a
we
positive
defined we defined W hat, I mean, new to be x transpose lambda I inverse.
Yes, we are defining a new estimator, but we will see like
Okay.
from where is this estimator coming, because the previous estimator W hat ML was like we were finding out the ML estimator of my W, and that's how we had this xx transpose inverse xy. But is there any other estimator which is estimating my W for which the mean square error is much lesser, right? So this is our goal right now. So, okay. So the W hat mean square error of W hat mu, which is sigma square sum over lambda I plus lambda. I is varying from 1 to n. This is lesser as compared to sigma square sum over 1 upon lambda I varying from 1 to n, which is nothing but mean square error of,
Got it. Now got it.
yeah. So because lambda is a positive quantity, this term is always going to be smaller. Now the question is, how are we getting this W hat mu? So we will use the Bayesian modeling for the linear regression problem now. So to do the Bayesian approach, to do the Bayesian modeling, what do we have to do? So my parameter, is still W that we want to estimate. This is what we want to estimate, right? And if we need, if we are going to use the Bayesian approach, then we need a prior for W, right? We need a prior for W. What we already know is that my y given x comes from a normal distribution with mean W transpose x and variance sigma square, right? So for simplicity, so if you're writing this, it means my epsilon follows a normal distribution with mean 0 and variance sigma square. Just to simplify the calculation, what we are going to do is we are going to assume sigma square to be 1. Right? This for just calculation simplification. Now this is something that we know. This is a likelihood basically. This is my likelihood. So the likelihood is, I mean, your samples are being generated from a normal distribution. So if we have to use if you have to find the posterior, I know a very good choice to make the prior for like the prior distribution for W would be if I choose the normal distribution itself as the prior distribution for W, right? Because I know for a normal likelihood, our conjugate prior would be again a normal distribution. So that would be a good choice to make, so that it just about estimating the like updating the parameters and not the whole distribution being like changed. So one choice of prior that we can think of is, let's say my W follows. So since W is now we'll have to treat W as a random variable. So my W will follow a distribution, and let's say this follows a normal distribution, and we are assuming that this W of like the mean for this W is not 0, and the variance is some gamma square I. Okay, so this is my covariance matrix. So this is what we are assuming. So the prior is W, which is following the normal distribution with mean 0, and the likelihood we know. Now, once we have the prior with this and we have the likelihood, what do we need to find out? We need to find we know that my posterior is proportional to
Prior times likelihood.
the likelihood times the prior, right? So what is the posterior? So posterior is, you want to know, like once you have observed the samples, which is x1, y1, x2, y2, so on till xn, yn, how what is going to be the probability of your theta? So in this case, it is W. So probability of W, given that you have this sample with you, x1, y1, x2, y2, xn, yn, right? This is my posterior. And I know that this is going to be proportional to probability of x1, y1, x2, y2, so on to xn, yn. Okay. Given this W, so this is my likelihood, and the prior is f of W of W. So I know that my likelihood follows a normal distribution. So we can just write this. So what is the likelihood will be? How does the likelihood look like? It will be product of I varying from 1 to n. This is a normal distribution. So 1 upon sigma under root 2 pi. So sigma is we are taking to be 1, right?
1.
So sigma we are taking to be 1, and 2 pi. Actually, you can say if you have a normal distribution, you know the distribution looks like 1 upon sigma under root 2 pi e to the power minus 1 upon 2 x minus mu upon sigma whole square. So again, this under root 2 pi is a constant, right? And since we are writing a proportionality constant, like since we're writing just the proportionality here, so we can ignore the constant. It's okay. So we'll ignore this 1 upon sigma under root 2 pi because it's just a constant for us. So what will be left is e to the power minus 1 upon 2. So now it is the labels you have is yi, and the mean for this is W
W
transpose
transpose X.
xi, right? And divided by sigma. Sigma is just 1, so that is gone. This is whole square. Now what is FW of W? So FW of W is again a normal distribution. So you have again e to the power. We can just ignore the constant here again. and e to the power minus, so here we have wi minus 0, so we can ignore that, and 2 sigma square, right? So this is going to be minus wi square upon 2 gamma square. This is our variance. And how will I vary? I varying from 1 to d here, right? Because this, where does w belong? Like if when we write the linear regression problem, my w belong to rd, right? It's in d space. So I is varying from 1 to d. Now what happens after this? So this we have
Ma'am, can you explain the above expressions once more, ma'am?
which
This
what we
one.
have just written.
Yes, ma'am.
So are you clear about this part?
Ma'am, can you explain once more? I understood that
Okay,
I'm
see.
not getting the one which got into in the bracket. How you get y1 minus w2?
Okay. So what was given to us, I mean, what we know is that my y given x, this followed a normal distribution, right?
Yes,
Mean
ma'am.
was w transpose x and variance was 1. So this probability, when you find probability for this data set, I know this is coming from a normal distribution. So the distribution, I mean, if when you find the distribution, this is the PDF. This is going to be 1 upon sigma under root 2 pi. So sigma is just 1. So 1 upon under root 2 pi e to the power minus 1 upon 2. Now you have y given x, right? So basically the distribution, now here your randomness is in y. So your yi minus the mean, and the mean is w transpose x. So it is just going to be for each data point w transpose xi divided by 1, a whole square. And since we are just writing the proportionality here,
Randomness in ma'am, one minute. Ma'am. Randomness in y. I don't understand what it. It should not be in x, ma'am. It should be in y.
yes.
Okay. Ma'am.
So your w is sorry, y is basically your w transpose here. I don't know. Yeah. So your y is basically like given x. So your y is basically w transpose x plus epsilon.
Yes,
Right?
ma'am. Okay.
So this was about this term. Now, if we look at fw of w, so what we had assumed is that this follows a normal distribution with mean 0. This is, again, this 0 is a matrix. I mean, not matrix, it's a vector, right? It's a vector in RD. So 0 is in RD. And this is sigma square I, which is a covariance matrix that we have given here. So this also follows a normal distribution. So when we have to write the distribution, I mean the PDF for this is going to be e to the power minus 1 upon 2, e to the power minus 1 upon 2, wi minus 0 upon sigma square I whole square, right? So everything will just go away when 0 is not there. So wi square upon 2 gamma square is what we have. And I is varying from 1 to d.
Okay, ma'am.
Is that okay? Yeah. So now if we write this term in the second part, so the second part, which is, this is basically e to the power w1 square upon 2 gamma square e to the power w2 square upon 2 gamma square, so on till e to the power wd square 2 gamma square, right? So it can be written as e to the power 2 gamma square sum over wi square, right? This is okay? D. So the second term, what we can write is, instead of the product part, we can write this as e to the power sum over wi square upon 2 gamma square, right? Now again, what is my wi square summation? This is nothing but norm of w, L2 norm of w. So this is e to the power L2 norm of w divided by 2 gamma square. All right, this is fine. Okay, so now what does my posterior looks like? So now my posterior, which is proportional to product of I varying from 1 to n e to the power minus 1 upon 2 yi minus w transpose xi square times e to the power norm of w square upon 2 gamma square. Okay, this is what it is right now. So this is my posterior. Now this is just the posterior the posterior distribution. So from here, we are not able to, we cannot say exactly what this distribution is, right? So to find the estimate, so we have, this is just the distribution. Now to find the estimate of my W, we know two ways. One is we can find the expectation of this distribution, or we find the mode of this distribution, which is maximum and posterior estimate, right? So since the distribution of this is something which we don't know, so what we can do is we can find the map estimate, maximum and posterior estimate of W. So we know that my W hat MAP is nothing but argmax of my posterior, right? Or f of W given my data set. And this is over W. So one more thing that we can add is to like get rid of this exponential term is we can add the like log over here. So if we take the log, what we will get is sum over minus 1 upon 2 yi minus w transpose xi whole square, where I is varying from 1 to n, and this we will have, what's the yeah, there's a minus term over there. No? Yeah. Okay. So this would be minus of norm of w square upon 2 gamma square. So this is my posterior looks like. So W hat MAP is basically argmax over W for summation minus Wi minus W transpose xi square divided by 2 minus norm of W square upon 2 gamma square. Okay. So this is argmax of this term. So this can be equivalently, what we can write this is we can convert the max to min. So this will become arg min over W of 1 by 2. Since 1 by 2, we can pull it out. So, or it's okay. So arg min of norm of, what now, sum over yi minus W transpose xi square divided by 2 plus norm of W square upon 2 gamma square. All right. So this is my W hat MAP. Now, how do you find uh, the, like, how can you find the W which minimizes this term? So basically this is my objective, right? So this objective, which is, and how can you write this objective as? You can write this, one way to write this is, this is basically my X transpose W minus Y norm square divided by 2, this is, right, plus norm of W by 2 gamma square, right? This is my F of W. So,
Yes.
so we can take the derivative. So in this case, it will be grad. We will find the grad of F of W, right? And what is the grad of this going to be? So this is basically your X transpose W minus Y, X transpose W minus Y, right? Plus 1 upon 2 gamma square of W. Now you can expand this term. So what you will get is, you will get X transpose W ka transpose, which is W transpose X minus Y transpose, and X transpose W minus Y plus 1 upon 2 gamma square, this. So you take the product and you will have W transpose XX transpose W minus W transpose XY minus W transpose X transpose W plus Y transpose Y plus 1 upon 2 gamma square norm of gamma square. This is still my F of W. So look at this. I mean, these two terms are basically equal, right? So this, I can just write this to be minus 2 times W transpose XY. So what we get FW as is 1 by 2 W transpose XX transpose W minus 2 W transpose XY plus W transpose Y plus 1 upon 2 gamma square norm of W square. Now we take the derivative. So take the grad of F. So with respect to W, so this is W transpose W. So basically this is 2 times W. So what we get here is XX transpose W. So 2 times it is, so divided by 2, it gets cancelled out. Then here it's just XY. And for this part, it is again 2 times W, and 2 gets cancelled out. So you have W divided by gamma square. So this is grad of F is what we get. Now we equate it to 0. So if we equate it to 0, what do we get? So XX transpose W plus W by gamma square is equal to XY, right? And we need to find W. So W is nothing but my XX transpose plus 1 upon gamma square inverse, this goes to the side, XY. XX transpose plus 1 upon gamma square. Yeah, correct. So this is my W that we get. So this is my W hat MAP. And see that this W hat MAP that we have obtained, this W hat MAP is same as what we had, the new estimator that we had taken, which is XX
Lambda I.
transpose plus lambda I inverse XY. So earlier the new estimator that we had taken was W hat new to be XX transpose plus lambda I inverse XY. So in this case, so you can write I here. So in this case, my lambda is basically 1 upon gamma square. This is what we have. Both the estimators are same. So if instead of W hat ML, if we use the ridge regression, the estimate that we obtain using the ridge regression, the mean square error we are able to reduce by some factor, right? So this is from the this is how this new estimator has come. Any doubts here?
No, ma'am.
Okay. All right. So once we have this new estimator with us, which is W hat MAP, now there we see that there is a constant. I mean, lambda, like when we define this new estimator, we had this lambda term over here, and we said this lambda is a constant, but greater than 0. It's some constant, and this constant is actually this is a hyperparameter. You can call it a hyperparameter or a tuning parameter. This is a hyperparameter. Now the question is, this W hat and mu is something that is reducing my MSE, but there again we need to give the lambda values. So like which lambda value should we give so that it reduces the MSE more, right? So like how do we basically decide which lambda to choose from, which lambda to choose? So for lambda, like for choosing this lambda, what we are going to use is the cross validation technique. Okay. So this cross validation technique is going to help us in reducing this, finding out a lambda, an appropriate lambda, which will help us in reducing the mean square error. Now there are two different ways, or in general, like how we do cross validation is that we split the data set, whatever data set we have, into two parts. So one is the training part and other is the validation part. So usually 80% of the data set we keep it for training and some 20% of the data set we keep it for validation set. And this validation set is something that acts as a proxy for data set. So what it means is like you have the data set with you. Let's say you have a data set with you, and when you fit a model on this data set, you need something on which you can evaluate, right? You can evaluate evaluate the performance of your model on some data set. But if you use the whole data set in training, you cannot use the same to find the like how well it works on your new data set. So that's why we can split my data set into two parts here. This is what we do in cross validation. So on this training data set, we fit our model, and whatever model we obtain, we use that model to check or to predict the mean square error on the validation data set. Okay. So this is my validation data set, and this is my training data set. So the two very popular cross validation technique that are being used is One is k-fold cross-validation. K-fold cross-validation, and the second is leave one out cross-validation. Leave one out cross-validation. So leave one out cross-validation in short is also written as LOOCV. Okay. In shortcut, you will see this written as LOOCV at many places. So these are two very popular technique for cross-validation. So what we do, let's first see what we do in leave one out cross-validation. So in leave one out cross-validation, suppose if we have, if my data set is x1, x2, yes, sort of.
Ma'am, I'm not able to understand that hypervariable and tuning thing. A bit, I'm not able to get it.
Yeah, I have just started, right?
Okay.
Yeah, I have just started. So, okay. So this is what we wanted to do is see. We had initially W hat ML, and next what we found is W hat new, right? And this was
Yes.
coming from my Bayesian approach.
Yes, ma'am.
So this was found in order to reduces the mean square error, right? But there again, you have this lambda term over here, which is a constant, correct?
Yes.
So lambda I inverse xy. So since, I mean, yes, the new estimator is going to reduce your mean square error for your this linear regression problem where you are estimating your W. But what lambda should you choose is the question, right? And this lambda is basically a constant, which we define it in such a way that this lambda should be positive number. So lambda is greater than equal to 0, and this is basically called a hyperparameter. So this is something which you're giving to the model. This is not a part of the model, but basically you are giving it later at a later stage to see what should be the ideal value of this parameter.
And this lambda is actually equal to 1 by gamma square.
1 by gamma square, yes.
And, okay.
We'll come, I mean, gamma again is a constant.
Okay.
So we'll come to that. We'll first stick to this new estimator that we have found. Okay. So how do we choose this? So the cross validation is something that generally we do in practice. Generally, this cross validation is used for this hyperparameter tuning. Okay. So for that, two very popular technique is k-fold cross validation, and one is leave one out cross validation. So now we'll see what exactly are these technique. So let's say the data set we have is x1, x2, so on till xn. And here my each xi is basically xi comma yi, because we are talking about the regression problem over here. So this is how my data set look like. Now, what we are going to do in leave one out cross validation is that in training, we are going to use n minus one of the data set. So maybe in the first time, we are going to use x1, x2, so on till xn minus 1 in the training. And for the validation, we are going to use whatever we have left, right? So in the first case, we have left my xn, right? So this is what we're going to use for validation. The second would be that I do it till xn, but what I have left is xn minus 1. So that I will use for validation, right? And like this, you will have n different possibilities. So n minus 1th would be, let's say, I have used x2 as the validation and remaining in the training. And the nth such case would be that I use the first term itself as the validation. So x2, x3, so on till xn. And for validation, I use xn, right? So this looks something like you have 1, 2, 3, so till n, right? So maybe in the very first case, you are going to maybe just keep this for validation and you're going to train on the remaining. Then the second case would be that 1, 2, 3, so on till n. So you're going to keep second for the validation on. So on validation as in like this is where you will test your model, whatever model you have fit. You will test its performance on this validation set. So for that, you are keeping the second data set for validation, and on the remaining, you're going to fit your model. And similarly, you can do it n times because you have total of n observations. So every time you can leave one observation and you fit on the remaining, keep a remaining n minus 1 as training. So you have 1, 2, 3, so on till n. So in this case, you keep this as this for validation and fit on the remaining n minus 1, right? So this is the idea. So now once you like fit your training, like fit your data, fit your model on the n minus 1 observation and validate on the nth observation, the just one observation, then what you do is you find the error for each of these. You need to find the MSE. You need to find the mean square error for each of these. So what will the mean square error for the very first observation, I mean the very first split that you have taken? So here, let's say once you train the model on this data set, let's say the model that you get is f1 hat. Okay. So if it is f1 hat and you have to validate on this xn, so the mean square error and what is my xn? Xn is xn comma yn. So mean square error would be just yn minus y hat of n, right? Where y hat of n is f1 hat of xn square. Because it's a regression problem, this is what we do, right? We try to minimize the sum of residual sum of square error. So this you find for every split that you have made. So in this case, you will have yn minus 1 minus y hat n minus 1 square. You do it for all the cases, and at the end you have y1 minus y1 hat square, right? So for each of the split, you get a mean square error. Now, at the end, the overall estimate, the cross validation estimate that you get for leave and out cross validation is, so the cross validation estimate that you get for leave and out cross validation is the average of all these mean square error that you have found, which is 1 upon n sum over yi minus yi hat square, I varying from 1 to n. Right? Or in place of this, I can just write mean square error. Of all the data points. So I think this was only better. Yi minus yi hat square. Okay. So this is the least square estimate that we get when we use the leave and out cross validation. This is a technique for leave and out cross validation. This is for regression problem, like when you do the class, when you come across the classification problem. In place of mean square error, you will have, I mean, you know, the loss function in case of the classification is something different, where you just basically check for the number of misclassified data point and you take the average of all that. So there, that with the change, here. Only this part will change. Okay. Since we are talking about the regression, so we have taken the mean square error. So this was about the leave one out cross validation. Now, once we move to the k-fold cross validation, k-fold cross validation. In k-fold cross validation, what we do is, as the name suggests here, that you are going to make, so you have n data point and n observations with you. So you have x1, x2, x3, so on till xn, right? So now what you are going to do is you are going to make k folds of this data set. So when you make k folds, each of the folds, we assume it of equal sizes. So let's say if I have a total of 100 observations and I want to talk about 10-fold cross validation. So what we will do is we will split my data set into 10 equal parts. So each part will be like one fold. So this will be like the one fold, let's say this is fold 1, this is my fold 2, this is my fold 3, so on till this is my fold k. Okay, so whatever number of data point, number of observations you have, you split it into k equal part and you create k folds. So whatever we were doing on in the leave or not cross validation, where we were keeping one, so here it was leave one out cross validation, right? So you were keeping one data point for validation and training on the other. So here what you do is, since you're talking about the folds, so you train your data set into k minus 1 folds. So train on k minus 1 folds and validate on the remaining k fold, on the remaining 1 fold, right? So let's say you train your data set on fold 1, fold 2, fold 3 up to fk minus 1. You train it on these folds and you validate on fk. This is one possibility that is there. Or you train on f2 to fk and you validate on f1. So when we say you train on the k minus 1 fold, so whatever data points you have in this k minus 1 fold, you train on these observations, and the model that you get from there, let's say I get fj, this model, this is a model that we fit. So now you use this model to evaluate its performance on the validation set, which is in this case is the kth left out fold, right? So this is the model that you have fit on the training data set, which is FAT, and use this FAT to evaluate, to check its performance on this holdout data set, right? So you will check its performance on this holdout data set. So again, you will do the same thing. We will find the error term on this holdout data set. So you will get, since this is k fold we're talking about, so overall you will do this process, repeat this process k times, right? And for k times you will have k different mean square error. So you will have mean square error 1, mean square error 2, right? And they will get mean square error, some k mean square error that you will get, because you have k folds and you do it k times. So you'll get k different mean square error. So what does the cross validation estimate of k-fold cross validation get is, this is nothing but you take the average of all these mean square error. So 1 upon k sum over, so whatever the mean square error you have, right? Where j is varying from 1 to k. So this should be the cross validation estimate for this thing. So this is how these two techniques work, the leave and out cross validation and the k-fold cross validation.
Ma'am, could you give some like a real life example of when we use this?
So usually, like, see, if you look at the leave or not cross validation, what is happening? Every observations that you have, you are going to keep every observation on hold once, right? So you have to fit the model n times on different data set, right? You are fitting a model on different data set n times. So this can be quite expensive in like, because you have to fit it many times. So this can be quite computationally, this is expensive. So leave and out cross validation is generally like, this is used when you have a smaller data set, let's say some 50 observation, 100 observations. So in that case, this works well. And in k-fold cross validation, like, this works like in practice. Usually, like, 5-fold cross validation or the 10-fold cross validation is what is being used, and this works better if you have larger data set. This works better, k-fold cross validation. There is again the whole concept of this bias variance trade-off. I think we have not studied in this week, but it will come again in the later weeks. Like, how does like, doing all this, we are trying to in some way reduce our variance and the bias and so on.
Ma'am, basically in this, by testing different model with the best model which fits, we will pick that. Is it
Yeah.
like?
Yes. Yeah, it works like that. Okay. So this was about the cross validation. Now we'll move to like regularization of the linear regression.
Ma'am, but how it is linked with that lambda which we are hypertuning, which we are seeing? Matlab, how it is linked with to that? We have started from that hypervariable lambda.
Okay, so we have not.
We are
Yeah,
doing.
go ahead.
How it is linked to that?
How it is linked to that? Okay. So see, lambda is what we have to find out, and to find the best lambda, you have to use the cross validation. So depending on different value of lambda you take, you are going to get uh, different cross validation error, right? Depending on the lambda that you choose.
Okay. Matlab, there is a probable range of the lambda from which I have to choose, or it is just hit and trial. Matlab.
This is hit and trial. So when you run the code, no, you have to like you have to give the value of lambda. Maybe you give a range of lambda, maybe let's say 10 to the power minus 3 to 10 to the power 3. This is the range of lambda that I'm going to give to our code, and then run this process and see which is the lambda that is best fitted for our problem.
Okay, madam. Because as such the equation, it is 1 upon lambda 1 plus lambda. So as large my lambda is, the better is the solution.
Yeah, the large my lambda is ideally the mean square error would be
Smaller.
smaller. But again, there is this whole thing of the bias variance trade-off also that we have not seen yet.
Okay.
So I mean, it shouldn't be also so high that your I mean, you know, right? The mean square error is also bias square plus variance.
Yes, ma'am. Yes, ma'am.
Yeah. So in that also we have to see.
Take
I
care.
mean, your model should not be very high bias, right? So so all that has to be checked.
Okay, ma'am.
Okay. So next is my the two popular regression method. Basically, this is a regularization technique. So one is the rich regression. Now we are going to look at regularization. So one is the ridge regression. And the other is the lasso regression. So again, the idea of this regression technique is you want to reduce the mean square error in some sense. Okay, this is the idea. Now, what is like when we looked at the linear regression problem, um, there my W hat ML was given by argmin of sum over W transpose Xi minus Yi whole square, where I is varying from 1 to n over W, right? This was when we were talking about the simple linear regression. This was our W hat ML. Now, the difference in this ridge regression and the lasso regression is that the new estimator that we had seen, which was coming from the Bayesian approach, is basically the estimator of the ridge regression. Okay, so what the ridge regression is that your W hat R, which is to denote the ridge penalty, this is given by argmin of over the W. So whatever you had in linear regression, simple linear regression, that stays, which is W transpose Xi minus Yi whole square, I varying from 1 to n, plus there's a regularizer term that we add, which is given by lambda norm of W square. Okay, so this is my W hat R, and this is called the penalty term or regularizer term. Penalty or regularizer. Okay. So basically, this term is getting penalized, saying what it means here is this lambda is a penalty parameter for this. And what it does is like the higher the weightage you give to this lambda, the more it shrinks my W towards 0, the more it brings my W towards 0. So that is what we want, so that because like as the lambda increases, your W hat, I mean W, the norm of W would go towards the 0. Okay, and this stays the same. Sorry, not this stays the same. Okay, wait, so this is my W hat R, right? And the lambda is my penalty parameter. Now what happens is when my lambda is equal to 0, what happens when my lambda is equal to 0? Any guesses?
Penalty is 0.
No, what happens when my lambda is 0? Your
It will
W,
be like a normal linear regression.
yes, this is what you will get, right? So, and now what will happen if you keep on increasing this lambda? So basically, this lambda, what it does is it basically as you keep on increasing the lambda, it makes this W hat R goes towards the 0. Okay. So as the lambda grows, my W hat R will approach to 0, basically. So in a sense, when the lambda is increasing, your the estimate. So like since we're talking about W here, so and it is in D dimension, so you have W1, W2, so on till WD, right? So most of the terms in this, most of the parameters W1, W2, WD, they will go towards the 0, right? But in rich regression, what also happens is that it never becomes exactly 0. It never becomes exactly 0. But it will, as the lambda increases, your W, like most of it, like most of the WIs will become very close to 0, is what you can think of. So when that happens, uh, the error term would reduces automatically, right? So this is what is happening in the rich regression. But when we talk about the lasso regression, uh, what we are doing here in this case is that, let's denote the W hat L is equal to argmin over W, sum over W transpose xi minus yi square plus lambda L1 norm is what we are going to use, okay? L1 norm is what we are going to use. So I is varying from 1 to n. So since in the rich regression, my estimates are never equal to 0, what happens in lasso regression is that it makes sure that some of my estimates becomes exactly 0. So when we look at this W, right, so W hat, you get some values over here. So whatever features are basically redundant, it will make that feature to be exactly 0. So we don't, let's say you have some 10 predictors in your data set, but not all the predictors is of use to us in predicting y, okay? So in that case, the predictors which are not important to us, we can make it just 0, like which are very less important, we don't want into the data set. So that predictor can become 0, and that will happen by putting some estimates of W's to be 0, right? So whatever variable is not important to us, that can be made to 0. So that way we'll have some simple model where we have less of these parameters. So that is the advantage of using this regression and the ridge regression and the lasso regression. So basically, they are used for like the feature selection. The lasso regression is basically used for the feature selection. Like in case some features are redundant for us, those features can be removed in a sense, right? So that is the advantage.
What about lambda, madam? What will be the effect of lambda on this? Lambda?
So yeah, so the lambda here, so lambda, as we see from these two, the lambda was nothing but 1 upon gamma square, right, when we solved for this problem, and gamma was basically the variance, so the gamma square, right? So in case most of our features are redundant, your not beta, your W will go towards 0, right? So if W will go towards 0, it means my lambda is higher. And when will lambda be higher? When lambda will be higher when you have lesser variance. So when sigma square, not sigma square, the gamma square is small. So if what you can say from here is when most of the features are redundant, my gamma square is going to be smaller. Right? My gamma square is going to be smaller. And when we had found this estimator W hat R, which was XX transpose inverse plus lambda I inverse XY. So here we had assumed, so this is 1 upon gamma square I, right? So we had assumed that my W follows a normal, I mean the prior assumption that we had made is that it follows a normal distribution with mean 0 and variance gamma square I. So we wanted, I mean, when we are saying that my W is following a normal distribution with mean 0, it means we want our W's to be in such a way that most of my like WIs is closer to 0. Like most of it is in a neighborhood, small neighborhood of 0 in a sense. So this is the assumption we had made while finding out this estimator. And this is exactly what my regression is doing it over here.
So gamma is small or large? It is
So-
small, so lambda is larger.
Yeah, gamma is no. So gamma. Okay, I'm getting confused. So this lambda is your basically this parameter, penalty parameter I'm talking about, and this is given by 1 upon gamma square, right? So as you increase your lambda size, like as you maybe increase your lambda size from maybe 10 to 100, let's say you put, so that will make your features more and more redundant, right? I mean, saying that, it means most of the W's, it will try to make it closer to 0.
No, it means when lambda is large, it means gamma is small, meaning all the W's will
Correct,
be
correct.
will be all the
Very
W's will be
very closer to the 0.
okay, right?
Yeah, because the variance will reduce, right, in that case, because this is variance basically.
Yes, yes.
So most of this would go like become very close to the 0.
So that is that this ridge regression, na, when they are close to zero, that
This
is.
is ridge regression, yes.
So what is lasso? In lasso, actually they become zero.
Lasso, they actually become 0. Yeah.
So some of them may not be zero. So some of them are zero and some of them may not be zero. So the ones which are not zero, they are also having larger, but all of them are having the same variance, like that is gamma. Some of them are
No,
zero
so
and some of
okay.
them are not
No,
zero.
so this thing. Hold on. So this lasso regression, right? The lasso regression we have not this estimator that we have found. This is not using the Bayesian approach. I mean, not using the this prior, which we had used for ridge regression. This is not using this prior. Okay. So the prior that we use in lasso is actually, so I think it's Laplacian. So the Laplacian prior you use. So both are the Bayesian approach. Both ridge regression and lasso regression are Bayesian approach. So using this Bayesian approach, both are basically in a way reducing my mean square error, right? But the way these estimators are obtained are different. So in ridge regression, the prior that you had assumed that my W follows was a normal with mean 0 and variance gamma square I. But in lasso regression, the prior that you choose for your W is Laplacian with some parameter. I don't remember the parameter exactly, but it follows a Laplacian distribution. And that's how you get a different estimator for your lasso.
Okay.
Okay.
But in this case, in the ridge regression case, typically the lambda is large. Lambda is large because gamma is small in the ridge regression.
No, it's not like that. I mean, you can't say that my a gamma or the lambda is small or large. I mean, it depends on like what lambda you have has been chosen, right? So you saw that when lambda is 0, it just become my simple linear regression problem, where it was my this was my original loss function, right? This was my original loss, and stay the same problem. But as you increase the value of lambda, it means it tries to make more and I mean, more and more, it tries to push more and more W towards 0. That's all it says.
Okay,
And
okay.
again, it will depend on like what lambda did you get after you did this cross validation. I mean, hyperparameter tuning and all that. What lambda did you get, right? Now in lasso regression, what is happening is, it is not that it is trying to push your W2 towards 0, but it actually is able to make some of the features exactly 0. I mean, some of the WIs to be exactly 0. So in that case, we are able to say for sure that for whatever predictor my W is coming out to be 0, those features are redundant for us. Those features are not important for us. So we are able to get a much simpler model and we can work on that. So whatever features are more important, we are just working with those features. So that is one benefit that we're getting from lasso regression. So in rich regression, only when lambda is actually infinity, then in that case, it is able to make some of the features to some of the W's to 0. Okay, only in this case when it is infinity.
That is when gamma will be negligible.
Yeah, the
Gamma
weight
will
is
be
between
negligible.
yeah, negligible.
Yes.
Okay. So geometrically, how can we see this is, so the rich regression and the lasso regression, they both can be put it into an optimization problem. So the rich regression, you can think of it as you want to minimize your original loss, which was my W transpose xi minus yi whole square, where I is varying from 1 to d and W belong to Rd. Now it is a constraint optimization problem because in ridge regression, you are restricting, I mean, you have this extra term, which is lambda of norm of W square. So
I
what
equal
you
to 1
want,
to n, right? I equal to 1 to n.
I equal to 1 to n, correct. Subject to the constraint that my norm of W, length of W, is less than theta. And you will always have a theta, like for any lambda you choose, you will have a theta. So this is some theta, means some value, you think of it like that. That you will get for any lambda, you will get such theta. So this is the way you can write for rich regression problem. Now, when we go to the lasso regression problem, I mean, then how it can be written in optimization sense is you want to minimize your W transpose xi. I mean, these are again the original loss that we had with this. So you want to minimize this, but the constraint now that you have is that my L1 norm of W, L1 norm of W is less than equal to theta. Okay, this is the constraint. So when we see it geometrically, what happens is that in the rich regression setting, you will have like, let's say this is my W hat ML. You will, so there are ellipses that are, these are the contours that you get for this W hat ML, right? And like wherever it touches the first, right? So this is ellipse that you're getting. These are basically the contours. And I mean, there's a mathematical proof like why are these contours elliptical, that we are not going to do. So this is basically norm of W square less than theta. And what is this? This is W1 square plus W2 square is less than equal to theta, right? So theta is basically your radius. This is my theta. Okay. And this is my W1. This is my W2. See, again, we are talking about only in the 2-dimension case. That is what we can plot. We cannot do even 3D, 4D. I mean, they are a little difficult to plot over here. So the solution that you get, I mean, the point of intersection of this ellipse and the circle is what is giving me the W hat R. Okay. But when we talk about this lasso, you had this circle. You had the circle. So in lasso, you have the condition is L1 norm is less than equal to theta. So that will look like you will get a rhombus over here. Okay? And this is my constraint space.
What is W1 norm, madam? What is that?
Okay, so W1 L1 norm is defined as sum over Wi, where I is varying from 1 to d. This is how you define L1 norm. You take the mod of each vector, each term, and you sum it over. So let's say my W is W1, W2, so on till WD, right? So if I have to find L1 norm of W, it is going to be norm of W1 plus norm of W2, sorry, mod of this, so on till mod of WD. This is the L1 norm. So this is also a measure of distance, just like the L2 norm, where you take the square and add, right? This is also a measure of distance, L1 norm. So, so in lasso regression, we have this L1 norm. Now, if we, again, we have this ML estimated over here, and we plot this contour, right? Maybe. Something like this you will get, okay? So in lasso regression, because you have this points, the edges, where it is like you have this edges, right, at this axis. So you have this point 4 coordinates with you. So what happens is, like, when you do this process, you will have like it will intersect the axis first in place of the curve. This is what happens usually. So that is why in the case of lasso regression, you are able to get some of the Wi's to be exactly 0, because it will hit this point many times. I mean, it will hit these points more often as compared to the curves, is what happens usually. So that is why we are able to get some features to be exactly 0. So this is my L1 norm less than theta. So like this ellipse will usually intersect at these corners. So that is why you're able to get some of the coefficient to be equal to 0. But when you're talking about the ridge regression to constraint, you have a circle with you, a circular constraint you have, and so that's why this intersection of the ellipse when you do with this circle, you're not going to get any sharp. I mean, you don't have many sharp points over there to for the solution to be exactly zero.
You
So
are saying the ellipse will intersect this square
square
at the
at the
corners, you
corners
will say.
more often. Yeah.
Okay.
This is very simple case of 2D plane. Now when you have 3D plane, 3D 3 dimension, 4 dimension, 5 dimension, your like there it is more visible, like that this ellipse is intersecting with the corners more often, and that's how we are able to get more of the most of the wi's to be equal to zero.
In this case, this is a 2D case, so only one point is becoming zero here.
But again, this is only two features we're talking about. So even if one feature become zero, so I mean one we are getting
Both
only
cannot
one.
be zero, of course. Both cannot be
Hmm.
zero. Either one will become zero.
Yeah. So we'll pick only one feature. So if we talk about, let's say this one, right? So there I know this is my W1, this is my W2. I know that my W1 is zero and W2 will be some value. So one feature is we can completely neglect. So we can just choose W2 feature. Okay. So this was about the ridge and the lasso regression. So basically, both the regression, both these different two regression, they are basically reducing our mean square error, and they have been obtained using some different prior that you can put on the W1, hence at some different results. And lasso regression is usually used for the feature selection. Okay. All right. So that was about week 6. Anything else?
Madam,
Yeah, yeah.
Madam, there was there in yesterday's quiz,
Mm-hmm.
the answer keys have been released,
Mm-hmm.
and one of the questions was asking about the variance along the first principal axis.
Mm-hmm.
I think the answer to that question is given as 43, 44, whereas I worked out it to be 18 point something.
Okay.
So I think
Wait. Mm.
Yeah, you
I
get
got
43.75 if you do not like minus the mu or center it.
yes. If you do not center it, then you will get. But if you center it, then you will get something like 18 point. I think that's the
I think
answer
I
I
had
got.
seen similar question in PYQ, and even in there they have not centered it.
So if the question doesn't say to center, I don't think it's required. But okay, we'll see. We'll see that part.
But if it is PCA, then you have to center it only. Then you
Not
can do, no, Madam PCA.
no, not usually. I mean, you can do it even without centering. Mm. We'll see this. I mean, we'll discuss the quiz one solutions.
I thought PCA first of all you have to center it and only then you can do the.
That was for the simplicity is what we were doing. That was for like it makes our it makes the problem a little easier when you center it.
Yeah, like whenever it is
But
there is
variance should not change
value.
by centering.
Yeah, yeah, exactly. We'll see. Maybe you check it once again. Or where are you
Yes,
going
ma'am. That
from?
is also a thing. Even if you don't center it, the variance will not change.
Variance should not change. Yeah, maybe you
Yes. So
check the solution once.
I did it 2 or 3 times. The answer is coming out to be 18 point something only.
Okay.
Whereas the answer given in the quiz solution is something like 43 or 44. I don't know.
We'll check. I don't remember the problem at the current moment. We'll check that.
Actually, 3 or 4 points given on a single line. There were 4 points given on a single line, and they were asking to find the variance along the first principal axis.
Hmm. Okay. We'll see this. I mean, we'll have one session where we'll do the we'll do it. We'll do this.
Okay.
Yeah. Okay. So we'll close the session for today, and we'll meet again for week 7. All right. Thank you, everyone. Thank you for joining.